Okay, session 2, we look specifically now about nonlinear modeling and performance assessment for frame structures, primarily beams and columns. So topics for the session, modeling and demand capacity calculation for beams and bending, the same thing for beams and shear, and columns, beam to column connections, connection panel zones, and a little bit about diagonal braces. And also do a couple of demos along the way. The scope, we're talking about frame components, beams, columns, coupling beams, diagonal braces, and also beam to column connections. There's a number of different component and element types. And for each component type, and hence for each element type, and hence for the structure as a whole, there's a couple of important things that we need. Reasonably accurate nonlinear force deformation relationships. They're never going to be accurate, they're never going to be exact, but if a beam or a column is exerting some forces on the structure, we'd like the force level to be reasonably accurate. And correspondingly, when we're calculating displacements for the structure, we'd like those displacements to be reasonably accurate, and if only, for example, so that P delta effects are calculated correctly. And so we'd like the stiffnesses to be reasonably accurate also. So a reasonably accurate nonlinear force deformation relationship. Incidentally, we have factors of safety to cover uncertainty, and there always will be uncertainty. And then secondly, we need reasonable deformation and or strength capacities. We'll never know the exact ductile capacity of a plastic hinge. We've got to make some reasonable estimate of what it's going to be. And again, we have or should have factors of safety to cover any uncertainty. Another point is that we must choose realistic demand capacity measures, and it must be feasible to calculate the demand values. And I'll talk about this a little bit later on, but it would be very nice to say, oh, yeah, let's use strain as the demand capacity measure. Great idea, except that it's not realistic. You cannot realistically calculate strain. Now, maybe you could establish a strain capacity without too much difficulty, but there is no way that you can calculate a realistic strain demand. You can't do it. It's too sensitive to too many parameters, and you simply cannot calculate a strain demand with any accuracy. Curvature is exactly the same. You might say, let's use curvature. No good, you can't calculate curvature. You can, however, calculate things like hinge rotations with reasonable accuracy. So those become more realistic as demand capacity measures. And then rather obviously the best model is the simplest one that will do the job. And when it comes to nonlinear analysis, as we'll see later on, and particularly for shear walls, a more elaborate model is not necessarily better. So let's look at modeling and demand capacity calculation for beams and bending. We're talking here about a beam in a frame. It's typically going to have some stiff end zone within the column width, and then some clear span distance, and there may be some transverse loads. In perform, the end zones are assumed to be stiff and elastic. They're not rigid in perform, they're just stiff, and you can control the stiffness if you want. And any inelastic behavior is going to occur in the clear span region. So really it's the clear span region that we're interested in modeling. And if we're looking at a beam force deformation relationship, don't worry too much about the details here. The top diagram shows the complete beam, and there will be some moment end rotation relationship for the beam as a whole. But the thing we're going to be working on is the moment versus end rotation relationship for the clear span. And the end rotation for the clear span is rather different numerically from that for the beam as a whole, but that's just a detail. And there's going to be some relationship like this. It's a matrix. It's no longer a single stiffness value, but there'll be some, if there's some increment in rotation, there'll be some corresponding increment in moment, and this will be governed by some tangent stiffness values. Once we've got this, we can get all the other structural properties from that. Now, there are 5 models that you might consider using. I'm going to go through the 5 models in order. The first one would be to use an exact model, where you would take a short length of beam, and you could calculate, usually without too much difficulty, a moment curvature relationship for that short length of beam. So it's usually not difficult to get the moment curvature, the MC relationship. Now, if you have an elastic beam, the rest is pretty easy. If you're, for an elastic beam, all you're interested in is this EI value here. The rest doesn't matter. It just goes on forever if it's elastic. So for an elastic beam, if you're given EI, you can use linear beam theory, which is just curvature is M over EI, and you can get the force deformation relationship for the complete beam, and you can use bending moment, usually at the ends, as the demand capacity measure. Very simple. For an inelastic beam, you might say, okay, why don't we just sort of use the nonlinear or the deformation counterparts of bending moment. Let's use a nonlinear moment curvature relationship as shown up here, and let's use curvature as the demand capacity measure. That would be sort of the natural approach, and this would be an exact model. The trouble is it's impractical. It's impractical for a number of reasons, and I can't go into details too much, but in your notes there is some additional documentation on this. Firstly, bending moment is a good strength measure, but curvature is a poor deformation measure. The reason, it's not difficult to get the curvature capacity. The problem, the curvature demand, is very sensitive to the shape of the moment curvature relationship. The key point, there is no reliable way to calculate curvature demand. And see the seminar notes for more details. There are other reasons. Exact theory for a nonlinear moment curvature relationship actually turns out to be very complicated, too complicated for practical application. And in any case, it's not quote unquote exact. If you have a moment curvature relationship which becomes horizontal, and sooner or later it will, exact moment theory exact beam theory will predict infinite curvature, which is wrong. That's not going to happen. So exact theory is not exact at all. It's horribly inexact. So basically, don't even think about it. It's not going to work. The second one is to use a finite element model, and just illustrated here with elements of different lengths. The finite elements use the moment curvature relationship for the beam. For a linear moment curvature relationship, you know that the finer the mesh, the more elements you use, the more accurate the solution. It approaches the exact linear theory. So you might say, great, okay, if for nonlinear behavior, let's just refine the mesh and we'll get more accurate results. Doesn't work that way for nonlinear. One reason is that as the mesh is made finer, the calculated curvature will get larger and larger and larger. And the smaller you make the mesh, the curvature, maximum curvature, just get bigger and bigger. It's very sensitive to changes in the finite element mesh. It's also sensitive to a number of other things. If you really want to be exact with nonlinear, you have to use a lot of really complicated fracture mechanics theory. It's not simple nonlinear behavior anymore. It's much more complex stuff, which is way beyond anything which is practical. So a finite element model may be good for linear, not so good for nonlinear. I'll say more about this later on when we talk about walls, because a similar issue comes up. A couple of other issues: it can be computationally expensive to use this finite element model. You can use it in Perform 3D if you wish, but as a general rule, this is not practical and is not recommended. The third model is a plastic hinge model, and this is just illustrated here. In a simple case, you have an elastic beam with a plastic hinge at each end. This is the column face, by the way, because we're looking at the clear span. A plastic hinge is literally a zero-length hinge, very much like a rusty hinge. It's rigid until you reach a certain moment, then it rotates. Then you push it back the other way, it locks up instantly, and then it'll rotate in the other direction. It's almost exactly like a rusty hinge. So it's initially rigid, and then it becomes nonlinear. The key point is you assume in this case that all of the inelastic deformation is concentrated in these hinges. This is an elastic beam, so you have concentration in the plastic hinges. That's approximate, very approximate, but from a practical point of view, it actually is a pretty damn good way of doing it. And realistically, this is about as good as you can get. The deformation measure is also quite simple. It's hinge rotation. If there is a problem if you have gravity loads, and it's indicated here, if you have not very much gravity load, so as your bending moment diagram when hinges form is like this, it doesn't matter, that's pretty close to straight. Anyway, you know the hinges will form only at the ends. If you have much larger gravity load, you could get the maximum bending moment near the middle, and you might have to use some additional hinges to capture that. This does get to be a problem. One of the problems indicated here, if you have hinge formation in the middle, and you push the structure in one direction, the hinges will form in the middle. If you push the structure back in the other direction, they'll form in the same direction, so the beam will sag some more. This way it'll sag some more, this way it'll sag some more. It'll progressively sag under cyclic loading, and you probably don't want to have that happen. So it's a good idea to avoid having hinges form in the middle anyway. Just incidentally, a plastic hinge model can be used for a reduced beam section. It's actually a natural application for a plastic hinge model. Is the center of the RBS would be here and here, and this is where you might position your hinges. And it's a natural application of the plastic hinge model. If you have some experimental results, you can process them to give the required hinge properties. I would, though, be careful because I've seen papers where the values are processed to give hinge rotations not at the center of the RBS, but at the face of the column. And in that case, you would need to put the hinge at the face of the column. But I think the more natural thing here would be to calculate the equivalent hinge properties at the center of the RBS section and position the hinge at that location. The fourth model is a plastic zone model. And instead of assuming a zero-length plastic hinge, we now have at each end a finite-length plastic zone, but with an elastic beam in between. So the inelastic behavior now occurs within a finite-length plastic zones at the ends of the beam. Now, in a real beam, you will get sort of plastic zones, but there's something happens in a real beam, they kind of spread. They're not fixed in length. And there have been some theories that seek to model the behavior in terms of a plastic zone which changes in length, but they're awfully complicated. They're really too complicated for practical application. So practically, I think you have to go with a fixed plastic zone length. The issue is how long should it be? I'll talk about that in just a moment. Deformation measure. You can either consider the average curvature over the plastic zone, or you can consider the rotation occurs within the plastic zone, a lot like a hinge rotation, and that's just the average curvature times the plastic zone length. So it's quite easy to calculate a demand capacity measure for this model. The big issue is the plastic zone length, and there's a really important point here is that you have a moment curvature relationship for the beam, or possibly you've used a fiber cross-section, which means that you're calculating a moment curvature relationship during the analysis. But there is a moment curvature relationship for the beam, and this is what you have to use in the plastic zone. And so you can't sort of arbitrarily pick a plastic zone length and then use the actual moment curvature relationship. I think you can kind of see if you use different plastic zone lengths and the same moment curvature relationship, you're going to get different behavior for the beam as a whole. So what you have to do is to pick the plastic zone length, which enables you to use the moment curvature relationship for the actual beam. And there's a basic rule for this, 0.5 times the beam depth. It's really rough, but actually it's probably not bad. And for practical purposes, it's probably about as good as you can do. There are a couple of ways in which you can do this and perform. I'll demonstrate this later. You can either use a curvature hinge that uses a moment curvature relationship, or you can use a fiber cross section in the plastic zone. In that case, the moment curvature relationship follows from the behavior of the fiber cross section. I'll talk about that a little bit more later also. Here's what a fiber section for a beam might look like. You simply divide the beam cross section up into a number of fibers, and you assign locations and areas to the fiber, and the moment curvature relationship follows from the fiber behavior. And the beam is assumed to be elastic or horizontal bending. In Perform, you can specify a variety of different material types for the fiber properties. You can use a concrete type material, a steel type material without buckling, a tension-only material, or material with buckling. You can specify a variety of different material types for the fibers. There's quite a lot of flexibility. Again, though, I'm not going to go do. I will do some examples later on, incidentally, of a fracturing connection model using a fiber beam. Plastic zone length, and don't worry about this. You can look at this in your notes. Pauly and Priestley do give a more refined recommendation for the plastic hinge length based on experiments of bridge columns, and it gives you this formula here. Let's not worry about the details. The last model is the chord rotation model, and the key thing about this one is that the force deformation relationship is now directly in terms of end moment and end rotation. Just moment versus end rotation. No plastic hinge rotation, no curvatures, just the overall behavior of the beam directly. If you look at the end moment versus end rotation relationship, the initial stiffness here is, it's basically 3EI over LI, assuming that this inflection point is at this location and is pretty much on the chord joining the two ends. And if this is in the middle, you're probably familiar with this, to be exactly 3EI divided by L over 2, or be 6EI over L, which is a common number. And then from there on, it becomes nonlinear. Perform implements this, I'll show later, using a thing called a FEMA beam model, which exactly implements the chord rotation model. And the same thing for columns. The reason why it's called a FEMA beam is because this is the only type of model which is actually covered in FEMA 356, or what is now ASCE 41. So looking a little bit more at the chord rotation model, basically it assumes that the hinges at the middle and the moments are the same at both ends. Strictly speaking, it applies only for that case. But you can apply it for other cases. And somebody asked me earlier, why, when you use a FEMA beam model, do you have two of them, one at the left end and one at the right end of the beam? The reason is that the moment strengths may be different at both ends, and also enables you to put the inflection point somewhere other than the middle of the beam. And so you have two of them, one at each end, and they can be different if you like, or they can be the same. So strictly speaking, it applies only to symmetrical beams, no transverse load. However, it's usually reasonable to assume an inflection point at midspan. Even if the beam is unsymmetrical, why not sort of assume it like that? It's good enough for practical purposes in most cases. Often the transverse load is not very large, doesn't have much effect. If it does, you can't really use this model. And the deformation measure now is directly the rotation from the chord. Theta is shown in the diagram there. And notice that if it was hinge rotation, it's like the plastic hinge rotation. Here we're kind of talking about the total end rotation. Now let's, those are 5 different models. I'll say a little more about them in a moment. Let's come back and look at capacities. And we've shown this diagram before. The ASC deformation capacities. IO capacity is usually the onset of visible damage. CP typically at the ductile limit, and LS typically maybe 75% of that. And you can use this for components of all types. And for example, if you have some experimental results, you could use this relationship to get appropriate deformation capacities. And ASC 41 gives capacities for many different components, but for beams and columns, it gives capacities only for the chord rotation model. If you want to use a plastic hinge model or a plastic zone model, or heaven forbid, a finite element model, you have to do a little of extra work to determine what the capacities might be. Here are some examples of the ASCE 41 capacities for chord rotation. And this is the ASC 41 moment versus rotation relationship. Yield rotation, plastic rotation is measured from the yield rotation, and these are expressions are in terms of plastic rotation rather than total rotation. Steel beam and a reinforced concrete beam. Steel beam first. ASC 41 gives the capacities as in terms of a ratio of plastic rotation to yield rotation. So for IO, it's 1, which means you can get to double the yield rotation. Life safety 6, you can get to 7 times yield rotation total. CP, it's 8, means you can go out to 9 times the yield rotation total. And it does vary with axial force, as we can talk about later, but ASC basically does this for all beams, regardless of the span to depth ratio and things like that. And this is just an example that ASC 41 is, in its current form, is really a little crude. So this is a one-size-fits-all type of capacity. It's probably going to get more complicated as time goes by. Reinforced concrete beam is a little more complicated because it's a common sense thing, is if you have a high shear force at a plastic hinge, that hinge is going to be more brittle than a hinge which has got a low shear force. So it's going to have a smaller capacity. So if you have low shear, the ASC 41 now gives you this as a total value in terms of rotation, not as a ratio. 1% for IO, 2% for LS, and 2.5% for CP if you have low shear, and rather smaller than that if you have high shear. Another thing you see here is these are really rather crude numbers. They're sort of 1.5 significant digits. This is a very complicated process to determine appropriate capacities. And ASC 41 doesn't say you have to use these. It says you can use these if you want to, if you have experimental data available to you to justify other values, you could use other values. But do notice this one thing, that the capacity is dependent on the shear force, which is rather important. Let's compare steel and concrete, and I just took here a W27 by 94. I don't know where I got 23 feet from, but if you look at from the previous slide, calculate the rotation capacities and compare the steel and concrete. The plastic rotation capacities for steel member based on ASC 41 would be IO 2067. Incidentally, there's a typo when you're in the printed thing here. It's got 0.067, but you can fix that. The concrete one is 0.01, so rather a little unusual. The ASC 41 allows for the IO case, rather larger hinge rotation for concrete than steel. For life safety and collapse prevention, there would be 0.40 and 0.54. These are roughly double the values for reinforced concrete. So some complications. Firstly, steel beam capacities. The values I just showed were for compact sections. If the section is non-compact, it's smaller. And if the axial force is large, typically this won't matter for a beam, but it certainly does for a column. The larger the axial force, the smaller the ductility. You tend to get buckling sooner. So the rotation capacity can depend on the axial force. Large compression axial force, smaller rotation capacity. Concrete beam, smaller if the shear force is large, and also if the axial force is large. So the rotation capacity for a concrete beam hinge can depend on both the shear force and the axial force. And I'll refer you to ASC 41 for details. Summary. Practical models for beams. The chord rotation model, you would use this as the first choice. The main reason being that ASC 41 will give you some capacities. It's also the simplest model. If that doesn't work, use a plastic hinge model. That doesn't work, use a plastic zone model. If it doesn't work, you might consider a detailed finite element model. but I don't think you'd ever consider using exact beam theory. Let's say a little bit more about fiber sections. I showed a fiber section for a beam just before. They don't apply for the chord rotation model. A plastic zone is a little bit like a hinge. If you want to use a fiber section, you have to use and perform a plastic zone model. And this would be the most likely use, I think, of a plastic zone model. If you have a zero-length hinge, you can approximate it using a very short plastic zone. Now, typically, I think you would use a plastic zone about 1/2 the depth of the beam, but I will show later on an example where you have a fracturing connection, a pre-Northridge type connection. And that's, it's kind of like a hinge, but you can model it as just being a very short plastic zone. You can use fiber sections for finite element exact models also. It's rather more expensive computationally than a hinge model, and so you'd only use it if you really felt it was necessary. It's another little bit here, and some engineers feel that this is really an important effect, and I'm inclined to agree with them, and it's something we need to be aware of because this is something which doesn't happen in linear analysis. If you have a reinforced concrete beam, then as it cracks, the neutral axis will shift to the compression side. Here's the center of the beam, the neutral axis will move up to here. An elastic beam, the neutral axis would be in the middle, but it moves upward. So the axis of the beam has to extend. If it can extend, it will, and the beam will grow in length. If it can't extend, if for some reason it's confined by a very stiff column, for example, or possibly by a floor slab or something, then it has to go into compression. And it becomes rather like a pre-stressed beam, and it becomes stronger. And it does a bunch of things. So that you have a compression force, pushes on the adjacent columns and may do some unpleasant things. There have been cases where it can tear a floor diaphragm apart from the axial growth. Near the corners of the floor diaphragm, it may actually crack the floor diaphragm and make it split. So some engineers believe this is a substantial effect. If you model a beam using hinge elements, you will not get axial growth. If you model using fiber sections, it will. So you have to be careful here. And this is not a matter of analysis. This is a matter of engineering. In order to use nonlinear analysis, you don't have to know much about analysis. That's a problem for people like me and put in a computer program. You have to know something about analysis. You don't have to be an analysis expert. In fact, it's probably an advantage if you don't know anything about analysis. You do have to understand nonlinear behavior. And nonlinear behavior can be very different from linear behavior. I have found from working with people using Perform that if I take an engineer who knows nothing about structural nonlinear analysis but does understand behavior, he'll catch on to nonlinear analysis and deformation-based design pretty fast. If I get some young PhD that did nonlinear analysis for his PhD but doesn't know much about nonlinear behavior, he can be a pain in the ass because he requires a lot of hand-holding. The important thing is not what you know about Newton-Raphson iteration or step-by-step methods, is do you understand nonlinear behavior? And it can be pretty damn complicated. Next topic, let's do the same thing for beams and shear quickly. Steel beams rarely yield in shear, but one exception would be a shear link in an eccentrically braced frame. Concrete beams are usually brittle in shear, and so usually you would want to design not for inelastic behavior in shear, but you want to design for essentially elastic behavior designed for strength. If you do allow inelastic shear, it requires a shear hinge, and it's like a plastic hinge, but it's shear rather than rotation. The demand capacity measure for deformation can be shear displacement across the hinge, or alternatively, you can actually convert it to shear strain by just dividing the displacement by the member length. If we look at a shear link in an eccentrically braced frame, roughly this is what happens up in here. You get shearing deformation in the shear link, assuming it's properly designed. And this is what the deformation might look like. And it does have some bending because there will be some bending moment, but the dominant deformation is likely to be shear. And the way in which you probably would model it would be with a stiff end zone if necessary, an elastic beam, a shear hinge, another elastic beam, and an end zone. Or you could put the shear hinge at one end. It doesn't matter whereabouts it goes along the length. It just looks better if it's in the middle. The ASC deformation capacity for this, well, let's look at this. Let's look at the shear hinge first. There's a number of things in this diagram. I'll come back to those in just a moment. If you look at the shear hinge, the plastic shear strain for yield and shear, and this is an adequately stiffened shear link, would be 0.5% for IO, 11% for life safety, and 14% for collapse prevention. That's a pretty big shear strain. So it's pretty generous. It's also necessary because these tend to be fairly short. The shear displacement is shear strain kind of the clear span length. But what if you have inelastic bending as well as shear? What I've got here is two things. The right-hand end first is a moment hinge. And this would be, if you think the shear link can yield in bending, and if a long shear link might do that, then you probably should model for bending, and you could put in a plastic hinge. That's one thing you might do. Or, working backwards, if you intend that the shear link yield only in shear and does not yield in bending, what you might do is put in a moment strength section, and then calculate the strength on that just to make sure that the strength demand capacity ratio is less than 1, which means a hinge does not form, a moment hinge. And if the demand capacity ratio is larger than 1, then a plastic hinge does form. This is not what you intend. You need to redesign your shear link. So this is the way in which you might model this, end zone, elastic beam, shear hinge, elastic beam, possibly a moment hinge, end zone, and then you might separately put a moment strength section at this location. In a concrete beam, sort of similar. You might have an end zone, a plastic hinge, elastic beam, a plastic hinge. And if you are, in the unlikely event you would allow inelastic shear deformation, you could put a shear hinge at the end, which is probably where the shear is, where shearing deformation is likely to occur. If you did not want shearing any inelastic behavior in shear, that would be the OR. You could put a shear strength section here, calculate the shear strength demand capacity ratio. If it's larger than 1, it indicates, in fact, a shear hinge would form. That's not what you want. You have to redesign your beam. There's a complication, is that the larger the hinge rotation, the smaller the shear strength. And again, I think you can see this intuitively. If you have a rotation at a hinge, it's going to degrade the shear strength. And it tends to look something like this. This is your shear strength capacity versus the hinge rotation demand. And it's one of many complex interactions that can occur. It's one of the biggest complications in nonlinear behavior, these interactions. This is one example. In Perform, you can consider this. However, you can only consider it for a shear strength section. You cannot consider it for in the current version of Perform, for a shear hinge. And I'll illustrate later on how that might be done. Let's look at this. Let's see how beams can be modeled using Perform. And all I'm going to do is look at some compound components here. Let's look at a chord rotation model. And I hope you can read this from back there. It consists of an end zone, a femur beam, and femur beam implements the chord rotation model. And there are two of them. And the reason is that they could be different strengths. In this case, they're not. They're the same. But they could be different. So you have one for the left end, one for the right end. And then you have an end zone at the other end. That's the simplest model. You might also have a plastic hinge model, an end zone, which lights up yellow. I hope you can see that. And then a plastic hinge, then an elastic beam, and another plastic hinge, and an end zone. But you now have to come up with a plastic hinge rotation and capacities yourself, because ASC 41 doesn't give it to you. It's actually quite easy to get it for a concrete beam, a little more difficult for a steel beam. Here's a plastic zone model, and this is one which is using a curvature hinge. And this is actually just a very simple one. This now it's not a rigid plastic hinge anymore. This is something where you specify a moment curvature relationship for the hinge. Now, I'm not going into the details. It's just a little variation on a rigid plastic hinge. But this one has got an end zone. Then it's got a short length of beam, and this is 6.73 inches long, which happens to be 1/4 of the beam depth. This is W27 by 94. So we're putting a curvature hinge at the middle of the 0.5D length, and these lengths are not to scale because right now I don't know what the span of the beam is. All I know that it's got some components. And then an elastic beam section, another curvature hinge. And the other thing about this is the curvature hinge has got a tributary length. And it would take me a little while to explain this, but basically it says that this 13.46 is 1/2 the depth of the beam. So it's actually saying, let's use a plastic zone here with a moment curvature relationship designed by this hinge. And let's make this plastic zone 1/2 the depth of the beam. So you position it 1/4 the depth out, you assign a tributary length 1/2 the depth, and you've got a plastic zone model. Next thing we can use is a plastic zone model with a fiber section, and here there's a short length of fiber section, which is now 13.46 inches, 1/2 the depth of the beam, and this is using a fiber cross section. And if you want to show the properties, this happens to have just 4 fibers, 1 for the flange, 2 for the web, and 1 for the bottom flange. You could use more if you want, but 4 probably is not a bad idea. The next one would be a finite element model, again using the same fiber section, end zone, and then some finite elements of different lengths, 6 inches, 13.5 inches, 27 inches, and 54 inches, and then the elastic beam in the middle is whatever is left. I don't know what the span is presently, so the elastic beam in the middle would be whatever is left. This would be a finite element model. And here's an example where the shear strength depends on the rotation. This actually is the end zone is a plastic zone model with the fiber beam section. And if I go to the strength section, what I've done is define a shear force strength section. And it just happens to be rather crude. It's got a strength of 100, and actually the strength can depend on the axial force. Let's not worry about that. What I'm interested in now is if I look at the strength section, it says the basic component for effective rotation on shear strength is from 2 to 2. Now I'm going to go back to this strength section and look at the rotation effect. I've specified some properties here, and let's not worry about the details. Just look at this diagram, which indicates that I can specify a shear strength factor which depends on rotation of an adjacent hinge or plastic zone. I've specified some rather arbitrary values here. Don't worry about the details. But you can specify properties which will modify the strength of the beam depending on the amount of hinge rotation. And when I come back to this model, what this is saying is that for this, let's do the first one. For this component, use the rotation from component number 2 to component number 2. I go back. Component number 2 is the inelastic fiber section at the left-hand end. So what it is saying is when you come to calculate the shear strength capacity at this cross-section, look at the current amount of rotation over this plastic zone. Using that rotation, go into the little diagram I had before, calculate the strength reduction factor in shear, apply that to the shear strength to get an effective, a reduced shear strength, and calculate the demand capacity ratio based on that reduced shear strength. It's just something that, it's an important effect. You could do it by assuming the worst case, and you could specify shear strength reduced by the worst Plastic, the worst hinge rotation you might expect, but this is a little more sophisticated. It will actually include the shear rate, the hinge rotation effect for you. Next topic is modeling and demand capacity for columns, and I'm going to talk mainly here about modeling. The basic models are exactly the same as for beams: chord rotation, plastic hinge, plastic zone, and then finite element or exact theory. Chord rotation is probably the one you'll use most of the time. However, the behavior is complicated by P-M-M interaction. And a number of things happen when you get P-M interaction. The moment strength depends on P and vice versa. You know that. We'll show the interaction surface in just a moment. We now have biaxial bending rather than uniaxial bending as in a beam, which is a complication. And most important, after yield occurs, after a plastic hinge forms, what does it do? It doesn't simply rotate. It's much more complicated than that. The shear behavior is also more complicated. You've got biaxial shear, and the shear strength can be affected by axial force, by moment, and also by hinge rotation. So let's look at your PM interaction survey. You're familiar with these. I'll just show some implications of these in just a moment. If we look at a steel beam, and we take just a short length of the beam, we can get a PM interaction diagram, which looks something like this. If the PM point is inside the interaction or yield surface, then the column is elastic. If it reaches the surface, then a plastic hinge forms. And the problem is, what happens when a plastic hinge forms? We'll talk about that in a moment. Concrete's a little different. You get an interaction surface looks like this. Let's look at a steel section. Just look at some simple aspects of inelastic behavior for a steel section. Again, it's a short length of beam. Pure moment, this means that you're increasing the moment out here. A hinge forms at this point, and it's just a moment hinge, just like a beam. If you have pure axial force, you're increasing axial force. When it yields here, it forms an axial hinge. A little bit of complication, though. Suppose you had just a tiny bit of bending moment to the left, then actually this flange will yield first and this one won't, so actually it'll start to rotate. And if it's a little bit to the right, it'll rotate in the other direction, so it's very sensitive. And you will not get an axial hinge like this because you generally can't accept axial forces of that magnitude in a column. But theoretically it can happen. So it's like an axial hinge. And if you have a combination of P and M, when you reach here, in this particular case, if you have P and M as shown, this flange will yield, this flange will stay elastic, so you'll get both rotation and axial deformation at the hinge. It's sort of interesting if you have a zero-length hinge and you get axial deformation on a zero-length hinge. How can that be? You know, it intuitively a little strange. It means infinite strain, but it really isn't that strange. If you have rotation on a zero-length hinge, that's infinite curvature. And infinite strain, infinite curvature, not really that much difference. If you cycle the inelastic behavior on a steel hinge or a steel short length of a steel member, let's increase the axial force to some value and then cycle the bending moment backwards and forwards. So you increase the axial force. When you cycle a moment to the right, this flange will yield. When you reverse the moment, everything will unyield, and the next thing will happen is that at point 2 here, this flange will yield. So when this flange yields, you get some shortening. When this flange yields, you get some more shortening. Cycle it backward to point 3. This flange yields still some more shortening. Cycle backwards to 4. This flange yields still some more shortening. It just progressively shortens if it's in compression. If it's in tension, it progressively elongates. So this is just one of the things that can happen. There is a method for analyzing this, and it's known in the academia as plasticity theory. It actually originates with the von Mises theory for yield of a steel material, and it's applied by analogy to a PM interaction surface or a PM yield surface for a steel column, and it works quite well. It's pretty good for steel. I can't go into it. There is in the notes, there's a discussion of plasticity theory you can read if you wish. Concrete section, similar kind of thing. I'm not going to go through it in so much detail, but now if we just increase the bending moment, what happens is the neutral axis shifts towards the compression side, and so there is some axial extension. So even with no axial force, there is some axial extension. If you were to increase the axial force to the balance point and then increase out to here, then you would get only rotation without any shift of the neutral axis. So this becomes rather more complicated. Now, the reason why this happens in a reinforced concrete column is not because there's plastic behavior, it's because there's cracking. And plasticity theory applies if you have plastic behavior, and it doesn't apply to cracking. So strictly speaking, although you can apply plasticity theory to this type of PM interaction surface, you really shouldn't. However, we still do. And it's, from a practical point of view, it's probably not bad, but it really, strictly speaking, is not correct. So if you look at PM models for column elements, each model, and I'm talking here about a hinge model or a plastic zone model or a chord rotation model, are all the same. You need two FD relationships, one for bending, one for axial force, and the linkage between the two is through plasticity theory. Chord rotation model, you have an end moment versus end rotation, which is just like for a beam, and axial force versus axial extension or shortening. Plastic hinge model, hinge moment versus hinge rotation, hinge axial force versus axial deformation on a zero-length hinge, which may seem a little strange. Plastic zone finite element exact models, moment versus curvature for bending, axial force versus axial strain, incidentally measured to the cross-section centroid for axial force. And if you use plasticity theory, you can link them together. An advantage of fiber section we'll see later on is it doesn't need plasticity theory. Column deformation capacity. Because of PM interaction, column hinges or plastic zones have both axial and bending deformations. But the deformation demand capacity measure uses usually only the bending deformation, just the rotation. You don't worry about the axial deformation. Your capacity is based on the rotation. A complication is that the bending ductility is smaller if the axial compression force is large. So the hinge rotation capacity depends on the axial force. And the second complication for reinforced concrete columns is it also depends on the shear force. And to some extent, Perform allows you to do this. I won't go into the details. ASC 41, concrete column capacity, gives bending capacity for chord rotation model only. And the way in which the rotation capacity varies is roughly shown in this diagram. This is the rotation capacity, and this is axial force. If you have low shear, then at zero force, this is the rotation capacity, and for a high shear force, it's 20% smaller. These are the values you would have for a beam. Those values apply out to P over 8 A sub G F prime sub C of 0.1. Then they start to decline, and for larger axial forces, you have rotation capacities about 75% of the beam values. And for details, take a look at ASC 41. An alternative plasticity theory is a fiber section. I've already talked about fiber sections a little for beams. The advantage of a fiber section in a column is that PM interaction is taken account through the behavior of the fibers. You don't have to use plasticity theory. Another advantage is that since it doesn't use plasticity theory, it also applies for a concrete column as well as a steel column, because it does model the cracking correctly. Shear in concrete columns, it gets a little more complicated than a beam. You're still going to have shear hinges, but they're a little more complex. Firstly, you have shear in two directions, and so you have an interaction surface. It may be circular, it may be elliptical, it may be some other shape. You have some control over the shape within Perform. The shear strength can depend on the axial force, and the shear strength can depend on hinge rotation. So you could take in some of these complicated interaction effects. So it's somewhat similar to in a beam, but with these added complications. Sort of models you might have for a column with shear. The one on the left here is where the shear must be elastic. You would have a PMM hinge at each end, or maybe femur column components, and you would have shear strength sections. It's supposed to remain elastic and shear. You put in a strength section, calculate the strength to demand capacity ratio. If it's less than 1, it doesn't yield in shear. If it's greater than 1, you've got to redesign the shear. If you want to have inelastic shear, then you put in a VV hinge, and you might also have moment hinges as well. Perform has a shear hinge with interaction, but it doesn't have axial force effect and shear effect and things like that. I'm sorry, it just has basically a fixed shear strength. It's unlikely, though, I think, that you would have inelastic shear in a concrete column. It's just not a good idea. Beam-to-column connections. Firstly, let's look at a beam which has got some end connections, maybe a bolted connection which is semi-rigid, or perhaps a pre-Northridge welded connection which may fracture. So the thing you might do one thing is you can use a semi-rigid moment connection. I'm talking here about Perform. It's got a semi-rigid moment connection which has got a moment versus rotation relationship like this. You might use this for, say, a semi-rigid bolted connection of some kind. You would have to know the moment rotation relationship for the connection, and you would put in a component here which does this. An alternative would be to put in a short, and this would be for the fracturing cross-section, a very short, say 1-inch long plastic zone with fibers which model brittle fibers for the flanges and ductile fibers for the web. I'll give an illustration of this in just a moment. And you might, in addition, also put in a plastic hinge if you like. So you can do that. You can sort of mix and match these components in different ways depending on what you think is necessary. If you look at a fiber section for a fracturing connection, you might make this length here just 1 inch. Just because it has to be a finite length. This is the depth of the beam. And notice that if a flange fractures, it'll rotate about the other flange. So the tension strain out in this fiber is basically a connection rotation times the depth divided by the length. Don't worry if you're worried about that. Forget it, don't worry about it. The important thing is this other diagram. For the flange, the way in which you can model and perform is with a concrete fiber to provide the compression. It's just because a concrete material is a compression-only material. That models compression. Probably make it very strong in compression. For tension, you could use a tension-only fiber, which has a very small ductile range and basically fractures. And this would then enable you to model a fracturing weld at the flange. For the web connection, which is more ductile, a more ductile yielding material, and you would do this using a fiber section. Connection panel zones. I think you're probably familiar that the loads on a connection panel zone is basically you've got moments and shears coming in from the beams, moments and shears going out of the columns, and basically moment is being transferred from the beams through the panel zone to the columns, or vice versa. The effect of this is it puts the rather large shear stress on the panel zone. Much larger shear stress and strain in the panel zone than in the adjacent beams and columns, and in fact in the opposite direction. And you get a distortion which looks like this, and so the angle between the beam and the column no longer remains at 90 degrees, and it acts somewhat like a semi-rigid connection. Panel zone modeling. Firstly, connection panel zones have much larger shear stresses than the adjacent beam and column members. For elastic analysis, you can calculate the shear stresses from the forces in the beams and columns. You don't have to have an explicit panel zone element. For an inelastic analysis, however, the panel zone may yield. In this case, it is necessary to have an explicit panel zone element. Perform makes it fairly easy for you to do this. I'm not going to go into the details. Concrete frames are more complicated, and I think typically, I think I'm correct on this, ASC 41 says that panel zones in concrete frames should remain elastic. this is what the panel zone element looks like, and don't worry too much about the details. It consists basically of 4 rigid links which are hinged together, and it has a nonlinear rotational spring which models the shear stiffness and strength of the panel zone. And this is covered in fair detail in the performed documentation. You don't need to worry about the details here. ASC 41 deformation capacities for panel zones. This is ASC 41. It's given, as before for steel, as a ratio of plastic to yield rotation. 1 for IO, 8 and 11 for CP. For a beam, these were, if I remember correctly, 6 and 8 or something like that. It allows you rather more rotation for than it would be for a beam. Now, I've put up here the FEMA 273 numbers, and actually I've done this for a couple of reasons. One is that Perform 3D comes with a walkthrough example, this CSI version of Perform. And when I put in that example, it was an old example, and I'd assigned capacities to the panel zones based on FEMA 273, and I didn't realize it had been changed for FEMA 356 and ASC 41. And so the thing says, well, these are the ASC 41 capacities. They're not. They're the FEMA 273 capacities. That's part of the reason. The other reason is just to indicate that how inexact a science this is. FEMA 273 was the precursor to 356. And it actually specified the rotation capacities rather differently, but if we use a 50 KSI steel, these are comparisons of what was allowed in FEMA 273 and what's allowed in ASC 41. And these are pretty big differences. I don't know why these differences occurred, but let's just indicate this is a highly inexact science because FEMA 273 is not that old. But somewhere between 273 and ASC 41, somebody decided that it was necessary to reduce the capacities by more than a third. So it's a pretty inexact process. So let's go back to Perform 3D again. I'm going to just show an example of used an inelastic fiber section to model a fracturing connection, pre-Northridge connection. And without going into details, I've got a tension-only material which is brittle to measure the tension in the flange. I've used a concrete material which is in compression, which doesn't fail in compression, and I've done this for both flanges. I've added a couple of web connection fibers which are more ductile. So it's an approximate model of a fracturing connection. And then I've run analyses, and I've run a pushover analysis in the H1 direction, and I'm going to plot the pushover curve. And there's some jiggles here. These jiggles occur where the connections fail. And without going into details, I can tell you by the time it gets out to the end there, every one of those connections has failed in tension. And remember this number, it's 0.45 G. There's a strength out here, about 5% drift. Okay, then I'm going to go to a second model. One thing I'm going to do is actually come to this beam, and I'm going to look at the axial force in the beam. But I have a rigid floor diaphragm there, and the beam cannot grow in length, so in fact it's fully restrained. So instead of growing in length, it goes into compression. And it goes into rather a large amount of compression, so this analysis doesn't look very good. So as a second thing, I said, okay, well, let's put in a PM hinge there such that instead of just being the axial force being allowed to grow without limit, it'll be limited by the PM hinge. So I'm going to open up here a different model. And properties, and again, this is the same beam. I'll show the properties. And the thing I've done in here is I put in a PM hinge based on a W27 by 94. Okay? And I do the pushover analysis again. And it levels out at here at about 0.32 G. The previous one was 0.45 G. So I've sort of accounted for some the axial force effects, but have I really accounted for them? I'm not really sure whether this is right. And it makes a substantial difference, by the way. And one of the things here is these things can happen when you do nonlinear analysis. So you have to be careful. It's not a matter of plugging into a computer program and doing analysis and believing the results, because you're just analyzing your model. You have to be a good engineer, and you have to understand what's going on behind those results. So I did a third analysis here, and what I did was I took the beams and I put in axial releases in the beams, so that even though they were restrained by the rigid floor diaphragm, they could have zero axial force because they had an axial release. And I'll do that with looking at a third model. And again, if we look at the properties, here I put in an axial release for the girder, which is actually, it happens to be it's a component in Perform, so it's an axial release with a zero stiffness. Okay, so now the beam cannot develop any axial restraint, and the connections are free to hinge. And I'll do the pushover analysis again. Whoops. It's 0.16 G, and then it fractures, and in fact, you've got to prop it up. It actually the load has gone negative. Now, I just toss this out to do two things. Firstly, so you can do this kind of modeling if you want, but you better be damn careful what you do, because I did 3 different analyses here. I got 3 completely different results, and quite frankly, I don't know which one is correct. But I suspect that what is happening in a real frame is there is some significant restraint being offered by the floor diaphragms. Not rigid restraint necessarily, but I suspect that in a building with pre-Northridge connections, that it does develop substantial axial compression in the beams as the connections try to open up. It stops them from opening up, and that may be what saves the building, because if it had this type of behavior, it would almost certainly collapse, I think. If you have a slender brace, you would treat it as a bar element with just axial force. Forget about bending. If it's very slender, you could use tension-only material, just a tension-only brace. If it's moderately slender, you could use a buckling material. What you do here is you specify material, and then you use it in what's called a steel tie element, which has got a material and has got some area. The demand capacity measure is axial deformation. A buckling restrained brace is rather different. As I indicated before, one of the things about a buckling restrained brace, it tends to get stronger as you cycle it. It's called isotropic hardening sometimes. And so Perform has a separate element for buckling restrained braces, which does have this type of behavior. Again, the demand capacity measure is axial deformation. You can use a fluid damper. In a fluid damper, the relationship in axial force and axial deformation rate, not axial deformation rate is usually nonlinear. And as indicated in the diagram below, and one of the reasons I guess I understand is that if it were linear and the earthquake was stronger than you expected, the force would keep on going up and you could break all the connections and everything. If it flattens out like this and the earthquake is rather stronger than you expect, well, the strength levels out, so you're not less likely to break all the connections. In Perform, the relationship between axial force and axial deformation rate is defined by a number of straight line segments. The usual thing is to have a curve in here, but you approximate this curve with a number of straight line segments. The demand capacity measures can be either axial deformation or axial force, probably both actually. You'd like to know that you haven't exceeded the loads on the connection, so you'd look at axial force, and you'd like to know that you haven't exceeded the deformation capacity of the fluid damper, so you would use axial deformation also. And incidentally, if you do a pushover analysis, there's no dynamic effect, and so if you have a fluid damper, it doesn't do anything. It has no stiffness in the pushover analysis. But Perform does have a little feature where you can estimate the extra damping which is provided by fluid dampers. And even though the pushover analysis doesn't have any strength from the fluid dampers, it does have an approximate method which will estimate the energy dissipation in those fluid dampers and will give you some rough idea of how much additional damping you'd get and what the effect of that, how much additional damping you would get. And to some extent, the effect of that damping, the effect of damping comes in when you calculate the performance point or the target displacement. It doesn't affect the pushover curve, but it can affect the target displacement. Non-slender brace is more complicated. If a brace, you know it doesn't buckle, and you can model it like a column. You might assume it remains elastic. You may allow it to form plastic hinges. If it can buckle, this is really rather tricky. What you can try to do is you can try to model as a number of elements as shown below, and you can rely on the p-delta effect to cause it to buckle. And Perform will, if you include p-delta effect in this, it can buckle the component, but it's rather complicated. It may not work, and you'd have to be rather careful in using this procedure. So a conclusion on this session, we considered models and performance assessment for frame components. In the next session, we do the same for shear walls, and shear walls are very, very different from frames, a whole different set of issues completely. We'll cover that in the next session. Questions?
I was just wondering what kind of strain hardening can you represent for the shear link element?
For
the eccentrically braced frames, so the shear link.
For the shear link, yeah. The question is, if you have a shear hinge for a shear link in an eccentrically braced frame, what sort of strain hardening? I think what you may be getting at is that I showed the hysteresis loop for a buckling restrained brace, which increases in strength. And I think that a shear link may do the same thing. And the shear hinge that we have doesn't do that right now. Okay. It does not give you hardening under progressive cyclic loading. It's on the list of things to do.
If I was trying to model some gross geometric deformations like foundation uplift or sliding, would I have to jury rig up something with beams and mechanisms to do that?
Yeah. Did you say gross deformations or
sliding and uplift and things?
Yeah, I would like to distinguish that they're not really large displacement effects. You don't have to do a large displacement analysis for this. If it's uplift on a foundation, basically that's kind of a gap type element, and you can do that. If it's pounding between a couple of buildings, again, it's a gap type element. You can do that also.
Okay. Yeah, Dr. Powell. And how to consider the buckle in a column?
You mean an actual column or a brace? It's a typical column in a moment-resisting frame. Yeah. Well, they don't buckle. They don't buckle. I don't think so. The frame as a whole can buckle. It forms plastic hinges and forms a mechanism, and the p-delta effect can cause the frame as a whole to buckle. But I think you'd be pretty hard-pressed to find a column in a moment-resisting frame where the column actually buckles as a pin-ended column. Well, I think I could be wrong, but if you have a moment-resisting frame, with that, not a braced frame, an unbraced frame.
Yeah, maybe with the shear wall moment frame, this kind of structure, column.
So something more now of a braced frame, so either braced by a shear wall or again, I'm not really sure they're going to buckle. It's kind of hard to get I know you have L/R ratios and things for columns. I'm not sure they ever really buckle. However, this gets into the class of problem that indicated for braces. It was the very last slide that I showed, is if it really is important and you have to model it, and it probably shouldn't happen anyway, you have to use a model of something like this, and it actually is a very difficult problem. There is no single simple element that you can use and perform which will buckle. Well, actually, if you could treat it as a buckling brace with only axial force, then you could do it. But if you have PM interaction that's got a lot of bending stiffness, but it still buckles, you could just treat it as an axial member, which has got something like this. And if you wanted some bending stiffness and axial buckling, maybe you could put two members in parallel. One of them you could have a column with plastic hinges but no axial stiffness, and you could put in parallel with something which has got axial stiffness and no bending stiffness, and maybe you could fudge it a little bit. But if you really want to model a braced frame or a column actually buckles, that's a tough problem, and I'm not sure exactly how to do it.
Dr. Powell, you touched briefly on diaphragms and how you modeled a rigid diaphragm, but I believe some design standards are getting away from fully rigid and fully flexible diaphragms to one where you'd want to model the stiffness, at least elastic stiffness. Is there any way to model that and perform? And also, there are some cases where you introduce elements, lateral resisting elements at various floors, and you may want to look at a link element in your diaphragm. Is it possible to look at that with perform?
I missed the last bit again because of the echo.
Perhaps a link element in your diaphragm where you introduce more stiffness at a lower floor if you have setbacks in your building.
Well, I don't have any, I will talk actually about floor diaphragms a little bit and shear walls. If it's not okay to assume a rigid diaphragm and you have to model as deformable, then you've got to model it using elements. And that's not an easy thing to do, and it does also increase the computer time rather dramatically, unfortunately. It can be done. The performer's got quite a number of elements that you could use to model deformable diaphragms. I'll say a little bit about it when we're talking about shear walls.
You talked about using strain demands, and that you wouldn't be able to realistically determine them, strain demands.
Using for frame elements.
For frame elements, for beams and columns. Even using the fiber models, you wouldn't be using fiber models?
Actually, this is a good question. I did say that strain was not a good demand capacity measure. Now, and I also said curvature wasn't. Now, if you use a plastic zone model, as I actually am inconsistent here because I contradicted myself, is if you use a plastic zone model, then you can use the average curvature over the plastic zone as an appropriate demand capacity measure. When I said that curvature and strain were not good measures, I was really referring, I hope, to the exact model where you try to predict the exact amount of strain. When you use a plastic zone and you use strain over a plastic zone, what you're saying is that the gauge length for calculating strain is the plastic zone length. And it's the same with curvature. Is you're not using the peak curvature, you're using the average curvature over that zone. That's okay. It's where you try to calculate when you're using bending moment, use the peak bending moment at the end of the beam as your demand capacity measure. If you extend that and say, well, I'll use the peak curvature right at the end of the beam, in that last millionth of an inch, that's not going to work. But if you calculate an average curvature and or an average strain over some finite length, like a plastic zone length, then it's okay. And we'll talk about this in the next session because this becomes very important for shear walls. Because in shear walls, you may quite likely use strain as a demand capacity measure, but you have to define your gauge length very carefully. It's not just any old strain, it's a special strain over a special gauge length, and we'll talk about that later.
Brings me to a second question. You showed us different examples.
I hear a voice and I don't know where it's coming from.
It's Still the same one. You showed us 3-4 different examples for types of beams we could use, beam elements we could use, and how we could set up a beam element using different components. Would there be one which you would say works better than the others? You showed one, for example, with a plastic zone, one with a plastic hinge. What is your opinion, if any, works better?
Yeah, actually, there is one slide now which, pardon me, sort of addressed. My first choice would be the chord rotation model if it works. If for some reason it doesn't work, my second choice would be a plastic hinge model. And if for some reason that doesn't work, my third choice would be a plastic zone model. I wouldn't go any further than that. Well, if that didn't work, my fourth choice might be a finite element model, but you'd have to be rather careful. In the finite element model, the thing you would have is don't have a finite element which is shorter than 1/2 the beam depth. That would, then you're probably okay. But you can get all sorts of strange results from a finite element model. I think that would be the hierarchy that I would choose.
But when you start the design and you are saying it doesn't work, what do you mean it doesn't work?
The question is it a reasonable model for you to use for your nonlinear analysis? Yeah, if you feel it's a reasonable model to use a chord rotation model, then I'd say use that. If you don't think a chord rotation model is reasonable for some reason or another, then take a look at a plastic hinge model. If you feel that is not reasonable for one reason or another, then take a look at a plastic zone model and just work down the hierarchy. Sooner or later, though, you've got to make a decision. It's got to be made. It's a decision. I said this before that you may have done a PhD where you did nonlinear analysis. That's not going to help you. If you're a good engineer and you understand behavior, that's what's going to help you. You know the things you want to calculate. You kind of get a pretty good feeling for what's reasonable. You have a look and see what's in the toolbox, and you're the craftsman. You go in there and you take out the appropriate tool. And there's no universal tool that does everything. You've got to be the craftsman and pick the proper tool. You've already had lots of chances. There you go.
You emphasize that it's very important to properly treat p-delta effects. And I'm just wondering, do you have to do something special to really model them properly in the analysis? Because from my experience, often you would have frames, say moment-resisting frames that are coupled with some gravity columns, and it's really moment-resisting frames that are taking care of this overall sway effect that cause additional p-delta effects. But often what I find in programs is that the tributary loads, the gravity loads that are affecting these effects are not adequately treated. So I was just wondering, how do you go about it in Perform?
So this is p-delta effect, Hofer. Exactly. Yeah, the question was, if you have a perimeter frame structure, so you have a lot of internal gravity framing, what do you do with p-delta effects? Well, the thing you do not do is model the external frame only and put on it only the loads on that external frame. That's wrong. You have to account for the p-delta effect of all of the loads on the internal frame. And you can do one of two things. You can either model the internal framing directly, and you may want to do that even though it adds more elements to the model. And then you put the loads on the gravity columns, and you'll get the p-delta effect from that, including maybe any torsional p-delta effect which may be present. The alternative is not to model the internal framing, but now you must put in a special p-delta column where you put on that column all of the loads on the internal columns, and that will provide you with the p-delta effect. It won't have any torsional stuff. It'll only be the translation, but the torsional usually isn't that very large. But the mistake is to leave it off. You must put it in.
I was looking at rocking structures, and I was just wondering what within the toolbox would be the best way to capture permanent settlement, vertical ratcheting down of the footing, not too dissimilar to the column with the plasticity theory.
So if you have a foundation which is if you have a foundation which is not going to go anywhere, then I think you can model it even with rigid supports or maybe with elastic springs. But if your foundation is going to have significant inelastic deformation, and I think you have to model it. You've got to put in models for the piles and things like that. And again, you go to the toolbox and you have a look and you see what might work. It is possible to model piles as columns and use bars to model PY springs for lateral displacement, and you can do that, and it makes the model more complicated. Of course, the answer is design the foundation so it doesn't do that. You would have to include the foundation in your model, and of course that makes your model more complicated.
Have you tried different models for different frame element? The one being from the other one with different model. Within
the same structure, you can do that if you want to. Yeah, people do that. It has been done. You don't have to use only the chord rotation model or only plastic hinge models. You can mix them. Different elements can have completely different models if you want. I was afraid your original question was that I did a comparison of different models as if they made very much difference, and that's a can of worms I'd rather not open. Let somebody else worry about that.
How does perform? What's the methodology behind that estimate?
For pushover?
For the pushover.
It's basically pretty straightforward. At any particular point in the pushover analysis, you know what the deformation is of each of the dampers. It also, at any point along a curve, you can make an estimate of what the secant period of the structure is. It's in the capacity spectrum method has this. So what you have is an amplitude of deformation for the viscous fluid damper, and you have an estimated period, so you can calculate the energy dissipation, and it just does that for you. And then when it's looking at the energy dissipation, it gives you the percentage damping estimated from inelastic behavior, and separately the energy estimated from fluid dampers. But it's all tied in with the capacity spectrum method, and as you're probably aware, the capacity spectrum method is a suspect method. A lot of people argue that it is simply not an accurate method.
Professor Powell, over here. If you have steel jacketing or fiber-reinforced polymer jacketing for a portion of the length of the column, how do you treat it in Perform 3?
The question was if you have steel jacketing or fiber reinforcement, from retrofit of a column. I think that would be a prime choice for a plastic zone type model, or possibly even a finite element model. I don't know. The problem you run into, though, is going to be the behavior of the concrete, because it depends how much confinement is being provided by the encasement. There's nothing that directly does that. Again, you go to the toolbox and you see what is in there that might enable you to solve that problem.
We've used drain 2D in the past to do something like that, and I don't know if the same input variables like changing the stress strain curve of the confined concrete can be imported into.
Yeah. So you say you've done it with drain in the past? Yeah. Anything you've done with drain, you can do with Perform. And Perform actually, to some extent, is based on drain 3D, but it's drain 3D on a heavy dose of steroids. I mean, it does way, 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 way more than. But anything you can do in Perform 3D, you can do it anything you can do in drain 3D, you can do in Perform.
Question.
Okay.
Now, I realize for the FEMA beam, you use the ASE 41 parameters for the moment rotation relationship. Can you not use that relationship for the plastic hinge as well?
Yeah, the FEMA ASE 41 gives you capacities for the chord rotation model. I can't go into the details here, but it turns out if it's a reinforced concrete beam, it's quite easy to get the corresponding hinge rotations. In fact, they're exactly the same as the rotation capacities for a reinforced concrete beam. For a steel beam, that's not the case because it's defined differently. But for a concrete beam or column, you can put in a plastic hinge or a PMM hinge, and basically you use the same rotation capacities that you would use for a femur beam.
Okay.
For a
That
chord rotation
Not
model.
the case for steel, though.
Pardon?
It's not the case for steel.
No, the reason is that the capacities given for the chord rotation model in ASC 41 are plastic end rotations directly. And it turns out they're the same as plastic hinge rotations. In fact, in the femur beam model in Perform, it actually converts to a plastic hinge model. But in a steel beam, there are multiples of yield. So it's not simply taking the same capacities and transferring them. It depends on the aspect ratio of the beam. You can do it, and I think it's in the documentation, is that Performer's got two types of hinges, a rotation hinge, and that's the one that you could use for reinforced concrete. And it has a curvature hinge. I did mention the curvature hinge in the context of using it for a plastic zone model. But it turns out that the hinge you need to use for steel is a curvature hinge. And you can, by using a curvature hinge, you can use the femur chord rotation values for steel without too much effort. Yeah, let me not say anything. I can get bogged down on that one. It's somewhere in the documentation, and it's explained how the femur model is implemented using plastic hinges, and it is explained in there. And using some reverse engineering, you could do it yourself.
Thank you.
In many cases, the failure of these elements has to do with fracture at net sections at bolts, buckling of rebar that then go through low cycle fatigue fracturing. How are these dealt with in these programs? Are they assumed that in new structures they're prevented, and that in existing structures you use FEMA curves? And if that's the case, would you say that the FEMA curves have a degree of confidence and development that's compatible with the degree of sophistication of the programs?
So the question is, if you get into like an actual collapse situation where you get,
well, basically fracture of elements as opposed to just slow degradation.
Yeah, so the question has to do with when something actually fractures. To start with, if you look at that YULRX, both the Perform and the ASC 41 force deformation relationships have brittle strength loss in them, which really kind of is intended to model fracture. And one of the things I showed you in the first session today, a hysteresis loop, and it started off as a nice fat loop, but when you actually got fracture, it was almost there was no loop there hardly at all. Now you can do this. Yes, you can model it. Now the question is, what does it mean? It becomes kind of a separate issue. As this may be going beyond what your question is, but I do see in the academic world it's incremental dynamic analysis being done, where the idea is to estimate when the structure will collapse. In other words, the limit state which is being used is collapse. And it disturbs me a lot because I don't think it's the right limit state to be using for this type of application. It's almost a garbage in, garbage out type thing. You're analyzing the model. I'm not sure you can model collapse with any degree of accuracy at all. I just wonder if you shouldn't use some limit state which is not quite at collapse. But coming back to the original thing is, you can model fracture. In the example I gave you with the pre-Northridge connection, the flanges were actually fracturing, and then the analysis was being considered taking that into account. If you really want to push the structure that actually collapses, I think you're asking the wrong question. I'm not sure that's an appropriate limit state.
Well, I was thinking that is an issue, but if you're trying to define your backbone curves as to where they drop off and you don't wish to go past that, how much confidence would you say we should be putting into the limits that are published in FEMA? Because I've heard comments about FEMA is too conservative, or in many cases they're judgmental. So we're sitting there with curves that are perhaps not as overly robust or under-robust, and we're applying very sophisticated analysis techniques to come up to these limits and use these cutoff limits. And I guess my question was, how much confidence would you say that we should have in those limits?
Okay, if you're talking about using FEMA values, I would hope that the ductile limits that are specified in FEMA are probably should, I think, be conservative because of the uncertainty. It's just a factor of safety issue. One of the things that concerns me, I'm not sure the answer to this, is this business of running 7 earthquakes and taking the average. If you're running the collapse prevention and you take the limit where the mean demand capacity ratio is right at the ductile limit, that means that there are some components which have gone beyond the ductile limit. Two questions arise. I mean, should you in the model account for strength loss or should you not? And secondly, is it a bad thing to allow some of these things to actually, some of the components actually to fail? I'm not really sure, it gets into a sort of almost philosophical realm. And clearly the estimating a ductile limit is a very inexact type science. You just have to do the best you can. It just comes back again as an exact analysis is literally impossible. This is an engineering problem, not an analysis problem. And you just have to make your best judgment. Also, you have to make clear to the client you can't guarantee performance. You're just saying you're going to give it your best shot. I'm not sure you sell that to a client, but it's as much art. There's a lot of science goes into it, but the design is as much art as science, isn't it? Any analysis program is a tool. Nothing more than that. It's a toolbox, actually. And one of the things I often think is, it's CSI. We manufacture hammers. We don't do carpentry, kind of thing. Sometimes I'm kind of glad I don't do carpentry. God damn, it's a difficult job. I'm going to be talking about modeling shear walls this afternoon, and it turned out that I need an example. So last weekend I modeled a shear wall. And it was actually turned out to be the first one I'd ever modeled. I'd kind of played around with it, and I've actually really done it myself. And it's really hard. It's not easy. Frames are easy. Shear walls, they're nasty.
Another question for you, Dr. Powell. Over here. It's a philosophical question of sorts. What's your take on doing gravity load only, lateral load only? Like it's very common in the industry, like you say, this is just a designated gravity load system, only lateral load system, as opposed to a combined model that takes both into account. I mean, I know you could do either one very easily, but just from a philosophical point of view, what's your take on it?
Well, for nonlinear analysis, running them separately is plain wrong because you're assuming superposition applies. Superposition applies in a linear problem. It doesn't apply for nonlinear. So you must apply the gravity first and then apply any lateral loads with the gravity already present. And to do it any other way is not correct.